So J incident, as I said, is the incident flux, number of incident particles per unit time per unit area. And of course, we know earlier we have studied about the solid angle. The expression for solid angle is given as r sin theta d theta r d phi divided by r squared. R squared will get cancelled. You have sin theta d theta d phi. So d omega will be sin theta d theta d omega d phi. Okay. So total cross section, we can, I have already told you, we have to integrate to get the total cross section, correct? So integrating this one will give you total cross section. Okay, so this is differential cross section. This will be your total cross section. So integration, that will give you total cross section. So just to substitute d omega, expression for d omega. Okay, so d omega will be sin theta d theta d phi, sin theta d theta d phi. Rest of the terms, let it be like this. And of course, we have two variables, theta and phi. Theta, the unit will be 0 to pi. Phi will go from 0 to 2 pi, which we have already studied in quantum mechanics 1 itself. So now separate. We just separate into theta term and phi term. So that will give you this expression. Any doubt? Very simple. And of course, d phi. When you are going to integrate d phi, that will give you 2 pi. So 2 pi. Rest of the terms, d sigma theta comma phi and sin theta d theta. Okay, is it okay? Your total cross section is given by this expression. The effect of potential is negligible because the incident particle is at the large distance from the target. Of course, it's very important concept we are going to discuss now. So we have, as I said, we have the beam of incident particles. So these particles will bombard with the target. Okay, suppose if it is too far, if it is too close, then there will be interaction between these two. If it is too far means we have r will be infinity. Suppose we consider r equal to infinity. The potential energy between these two, the expression will be V of r equal to minus e squared by epsilon naught, 4 pi epsilon naught r. Correct? We have already studied. And r tends to 0, then V of r becomes 0. So we are going to neglect the potential energy term. Is it okay? If it is too close, it's okay. If it is too far, when r tends to infinity, we are going to neglect the potential energy term. So we know already about time independent ordinary wave equation. We know already this. Kinetic energy plus potential energy equal to total energy. So now we are going to discard the potential energy term. So we are going to have only kinetic energy will be your total energy. Is it okay? Okay. Arguing this r tends to infinity. So multiply on both sides by minus 2 mu by h bar squared. As I said earlier, so we have used only mu instead of m. In quantum mechanics 1, we have used only m. It's a single body problem. Now we are going to study two body problem. Scattering theory is a two body problem. Two body problem, we will have to use only mu. 1 by mu equals 1 by m1 plus 1 by m2. Okay, so mu equals m1 m2 divided by m1 plus m2. So there will be two particles. Incident particles, so target particles also will be there. So there will be two particle system. Okay, so we will have to, suppose we want to convert into one body problem, we will have to replace m as mu, m by mu. So minus 2 mu by h bar squared, on both sides we have del squared psi incident of r, which is equal to minus 2 mu by h bar squared psi incident of r. Is it okay? And instead of this, we can keep as k naught squared, where k naught is the wave vector of the incident particle. K naught, wave vector of the incident particle. So this expression 6.8, equation 6.8 is, we have del squared psi incident of r plus k naught squared psi incident of r equal to 0. Is it okay? And this expression, this equation already we have seen in mathematical physics. We have seen already this one in mathematical physics. Can you remember this expression? This is Helmholtz equation. This expression is known as Helmholtz equation, for which we have the solution as Green's function. Can you remember? So Green's function. So the solution of Helmholtz equation will be Green's function, which we are going to use Green function maybe later in the next class. Okay. The solution of this Helmholtz equation will be Green's function. Okay. A two particle collision takes place, as I said earlier. So in the scattering experiments, hence a reduced mass mu is used instead of m. So k naught is a wave vector of the incident particle, and the solution of this will be your a e power I k naught r. Okay, what is this equation? Can you remember? What is this one? A e power I k r. What is this one? Plane wave equation. Very nice. So all incident particles will be plane wave in nature. So this is what I said earlier. Can you remember? Incident particles, the wavefront will be plane wave. The solution of this equation is a plane wave equation. So A e power I k naught r. K naught is the wave vector of the incident particle, and this expression is known as plane wave equation, where A is the normalization constant. Parallel beam of incident particle is represented by a plane wave. So this is your plane wave equation. Okay. And of course we know that the momentum of the incident particle, as I said earlier, incident particles surely will have definite momentum and energy. Okay. So momentum will be, your P will be h bar k naught. So after the scattering, so what will happen? The scattered particles will be absorbed by a detector, a suitable detector, which will be kept too far away, and that will have a spherical wavefront, and this is the expression for a spherical wavefront, e power I k r by r. Instead of k naught, we have written as k. So k is the wave vector of the scattered particle, k naught will be wave vector of the incident particle, k naught and k. So you have to differentiate these two. And here a e power I k dot r by r. Can you remember? Sin k r by r. So this is a sphere one. Can you remember? Which we discussed earlier in mathematical classes. So similarly, this will be your spherical wavefront. Okay. So its amplitude depends on theta and phi. Your scattered wave function is nothing but this expression. So this is your scattered wavefront. So scattered waves. So spherical waves. A f of theta comma phi e power I k dot r divided by r. This f of theta comma phi is nothing but your scattering amplitude. So we are going to discuss two models in future. One is Born approximation, another one is partial wave analysis. We are going to discuss these two models. We are going to get the expression for scattering amplitude. Square of the scattering amplitude will give us differential cross section. Differential cross section can be observed through experimental side, whereas scattering amplitude can be observed by theoretical side. So we are going to equate these two. So this is the idea. So k is the wave vector associated with the scattered particle. Theta is the angle between k and k naught. So your total psi will be very important one. Often will be using later in few due courses. Your psi of r will be the total wave function be incident particle plus scattered particle. So it's a combination of linear combination of these two, superposition of incident particle and scattered particle wave functions. Okay, so your psi of r tends to infinity, asymptotic solution as we said. So which is equal to, you combine these two. So we have the expression for psi incident, the expression for psi scattered. You add these two, keep a as constant out. So that will give you this expression, and this is your incident wave, and this must be your scattered wave. So this is your plane wave equation, and this must be spherical wave equation. So that's all. So your total psi will be this expression. Okay, equation 6.12. So this is the idea we have learned so far. The incident beam is parallel wavefront. The scattered beam is spherical. So spherical wavefront. The effect of potential is negligible. Correct? The effect of potential, that's why V of r equals 0. Can you remember? Becomes the incident particle is at the large distance from the target. The scattered particle is directed at a distance far away from the scattered. So it must be kept too far away. As I said earlier, suppose if detector is nearby and this will be burnt. So people keep only the target, the detector too far away. So they are all undeflected waves, unpolarized waves. Okay, so they are all spherical radial waves. So this is another schematic diagram of a scattering of a particle with a central potential. Okay. Very important section B question. The relation between scattering amplitude and differential cross section. The relation between scattering amplitude and differential cross section. Okay, very important question in section B. And of course we are going to have the derivation we are going to take from the equation of continuity. So that is the equation of continuity which you have already studied in quantum mechanics 1. Okay, del dot j plus d rho by dt equals 0. Can you remember this one? And j stands for your current density, rho stands for probability density. Okay, so we have taken only from consideration of probability equation, del dot j plus d rho by dt equals 0. The expression for your j current density is given by this. We have already studied in quantum mechanics 1. Okay, so current density is given by h bar divided by 2I mu psi star del psi minus del psi star psi. So you have to remember this one. The idea is, first we are going to substitute psi incident, get the expression, and we are going to get one expression, okay, for psi incident, and after that we are going to substitute psi scattered and get the incident. So that will be your j scattered, and here that will be j incident. Okay, and we are going to use the previous equation 6.2, and we are going to get the relation between these two. So that's the idea. Okay, we'll see. So psi incident we know already. Psi incident is given by a plane wave equation. So we know already a e power I k naught r. So psi is known, correct? What would psi star? We just take the complex conjugate of this. What would your del psi? Differentiate with respect to r. That will give you del psi. Take the complex conjugate, that will give you del psi star. Substitute all the expression, get the current density, J incident. That's all. Okay. So your psi incident will be a e power I k naught r. So just differentiate. Differentiating with respect to r, as I said. When you differentiate, that will give you I k naught. Okay. So a I k naught e power I k naught r. So this is over. This is over. Now just take the complex conjugate. When you are going to take the complex conjugate, your a will be a star. You have to take the complex conjugate, and of course, so that will be e power minus I k naught r. Take the complex conjugate of this, that will give you this expression. Okay, minus a star I k naught e power minus I k naught r. You substitute all the expressions in this equation 6.12. So we know already expressions, all the expressions, correct? Psi star here, del psi is here, del psi star is here, and psi is here. So we can substitute all the expressions. So this is the previous equation. We have substitute for psi star, del psi minus your del psi star psi. Just multiply these two. Here it is minus, this is plus. So that will give you 1. So the answer for this one will be 1. Remaining term will be a star. A star will be mod a square, which you have learnt already. So mod a square, and of course your I is here, k naught is here. Okay, minus plus. Remaining term you can have a star and a, that will give you mod a square. Your k naught is here, your I is here. So add these two, that will give you 2i mod a square k naught. So 2i mod a square. Your h bar is here, correct? Your k naught is here, divided by 2i mu. Any doubt? And these 2i will cancel, you have remaining term. So j incident will be h bar k naught mod a square divided by mu. So equation 6.18. Any doubt? So we will be using this expression later. So remember this one. So 6.18. Any doubt? So we have calculated now j incident. Similarly, we can also calculate j scattered. We will have to use j scattered. We will have to use psi scattered, the wave function of scattered, the scattered wave function. So this will be scattered wave function. So this is your scattered wave function, correct? So this will be a spherical wave function. Earlier we have used plane wave. Okay, this is for j incident, and this is for second one. So scattered one. Okay. So now del psi. Your psi is here. Del psi will be here. You have r in the numerator as well in the denominator. So we will have to differentiate carefully here. So earlier e power I k naught r alone. So we have differentiated easily. Now here r is here in the numerator, r is here in the denominator. So we will be more careful while differentiating. So now keep this as constant, you just differentiate. So that will give you this expression. Okay. Keep this as constant. You have to differentiate e power I k r, that will give you I k e power I k dot r. So remaining thing we have written. 1 by r, differentiate now, keeping this as constant. So when you are going to differentiate 1 by r, that will give you minus 1 by r square. So minus 1 by r square. Is it okay? Any doubt? I repeat. So r we have kept constant. We will differentiate. We have differentiated. Then we'll have to differentiate the numerator. We'll have to keep the numerator constant. So we have kept the numerator constant. Differentiating the denominator 1 by r, that will be minus 1 by r squared. So this will be your expression. So your del psi scattered is over. Similarly, go for psi star scattering. Just take the complex conjugate of this. Take the complex conjugate. So a star, that will be exactly like this. E power ikr becomes e power minus ikr. That's all. Now we'll have to differentiate as usual. So we'll have to differentiate the same equation. We'll have to differentiate as usual. We'll have to keep numerator constant. No, we'll have to differentiate the numerator keeping denominator constant, and we have got the first expression. And second one will be we have differentiated the denominator keeping the numerator constant. So we have obtained the second term in equation 6.23. Any doubt? Now almost we have got everything. Psi star del psi minus del psi star psi. We have already almost got all the expressions. Correct? So substitute. We will substitute now. H bar divided by 2 I mu. So this is the current density expression, and this will be your psi star. Okay. This will be your del psi minus. So minus is here. Minus is here. This will be your expression for del psi star, and this is expression for your psi. So now multiply. So multiplying this term will give you the first term. Multiplying this term will give you the second term. And minus, you pull minus sign out. So that will be plus. So multiply this term will give you third term. Multiplying these two terms will give you last term. Okay. Now we just multiply these two. So we will become a star. Of course, a star will be mod a square. And f of theta multiplied by f of theta will give you f of theta comma phi mod square. You have ik is here. This multiplied this will give you 1. R multiplied by r will give you r square. So minus, multiply this one will give you this term. Similarly. Any doubt? Just multiply. And multiplying these two, that will give you 1. R multiplied by r will give you r square. This will be a plus. And here also, multiply these two will give you 1. R multiplied by r squared multiplied by r. So you have r squared multiplied by r will give you r cube. Similarly here also r cube. And this is minus, this is plus, both will get cancelled. So in sky scattering we are going to add these two similar terms. Any doubt? We are going to add these two. So when we are going to add these two, we will get exactly this expression, equation 6.26. Any doubt? These two and I will cancel. So you have J scattering will be this expression. So you remember this one. So we have computed J incident, we have computed J scattering. Our aim is to find out the relation between scattering amplitude and differential cross section. It's a very important section B question, as I said earlier. So now we are going to use the expressions which we learnt earlier about dN. Can you remember this one? So number of particles scattered into an element of solid angle d omega in the direction theta comma phi passing through the surface element ds, which you have seen already in the figure, dA. Can you remember dA equals r squared d omega per unit time is given by this expression. So dN theta comma phi equals j scattered r squared d omega. So dN by d omega will be j scattered r omega. The expression for j scattered will be this expression. You substitute here. So we will get dN by d omega, which is equal to this expression. This r squared will cancel. So we will have this. We know already this differential cross section, which is 6.2, already we have learned. D sigma by d omega, which is equal to 1 by j incident dN by d omega. So you cross this one, just to bring this term to this side. So j incident d sigma by d omega equals dN by d omega. And of course, differential cross section, the definition for differential cross section is given by number of particles scattered into an element of solid angle d omega in the direction theta and phi. As I said, theta will be polar angle and phi will be your azimuthal angle. Okay, now just use equation 6.30. 6.30 is given by this. So now J incident d sigma by d omega, which is equal to dN by d omega, but dN by d omega is given by this expression from earlier 6.2. 30, which I have written here. You substitute these two. This r square will cancel. Okay, and so now just you have to use equation 6.18. 6.18, I have already told you that we will be using 6.18. Can you remember? 18. J incident equal to h bar k naught mod a squared by mu. So J incident will be h bar k naught mod a squared by mu. Okay. Now just take h bar a squared by mu this side. So J incident divided by k naught. So our aim is instead of h bar k by mu, we are going to substitute in this expression. I repeat, we are going to use 6.18 equation. 6.18 equation is this one. In this expression, h bar mod a square divided by mu equals J incident by k naught. So this term can be replaced by this term in this expression. Is it okay? So instead of h bar k divided by mu, we are going to use J incident by k naught. These two equations, let it be like this. So J incident d sigma by d omega, which is equal to this one, J incident by k naught remaining term. J incident by k naught remaining term. Remaining term will be k into this one. So k into scattering amplitude square. Any doubt? This one and this will cancel. So we have d sigma by d omega equals k by k naught f of theta comma phi. So this is the relation between scattering amplitude and differential cross section. So this is your differential cross section. This will be your scattering amplitude. Square of the scattering amplitude will give you differential cross section. This is the experimental side and this will be your theoretical side. The experimental can be observed differential cross section easily. One can observe the experimental side and this will be your theoretical value. And for any elastic scattering, k equals k naught, which you have already learned, correct? For any elastic scattering, the kinetic energy of the incident particle is equal to kinetic energy of the scattered particle. So if kinetic energy equals, so momentum will be equal. So momentum of incident particle will be equal to momentum of the scattered particle, correct? So momentum, the expression for momentum will be h bar k naught, which is equal to h bar k. H bar will cancel. You have k naught equal to k. So k naught equal to k for any elastic scattering. So if it is so, will get cancelled and we will have this expression. So this is the expression for the relation between differential cross section and the scattering amplitude. Okay, as I said earlier. In order to determine the differential cross section, it is enough to know the scattering amplitude. So if you know scattering amplitude, the square of scattering amplitude will give you differential cross section. In fact, see earlier we said theta comma phi. We have omitted now phi. The reason is, since the energy is assumed to be spherically symmetric, the scattering amplitude is independent of azimuthal angle. So it depends only on theta. It does not depend on phi. Okay. And very important thing is, one more question, as I said earlier, the total cross section, differential cross section, the unit will be L square. And of course this is L square. So the unit of scattering amplitude will be L. So that's why L square. So L square and L square. So the unit of scattering amplitude will be L. Differential cross section will be L square. So don't forget. So now we are going to get in due courses, we are going to get the scattering expression for scattering amplitude by means of two big questions. Okay, two experimental side. One is Born approximation method, what we call this high energy scattering. Another one is partial analysis. So they are all theoretically based ideas. Okay, theoretically based ideas. We are going to get the expression for scattering amplitude. Square of the scattering amplitude will give you differential cross section, which we are going to obtain in the experimental side. Okay, so Born approximation is nothing but high energy scattering, and partial analysis will be low energy scattering. And this is applicable for weak potential, and this is applicable for all the potential. So that's the difference between these two, which we'll see later. Okay, so that's the idea. And today we'll wind up, and tomorrow we'll discuss the Born approximation. Okay, so thank you, students.